All right, well, hope everyone is well. It's a beautiful winter day, and I am hanging out by the fire outside my home. And of course, birds keep screaming at me, but they're just mad because they started off as engineering majors, and I guess they changed the business, and now they're just screaming at me every now and again. But let's see how this goes. So we're still in section 1.3. We are trying to get a feel for a few ideas. More importantly, we want to get a feel for the nature of vectors, the idea of a linear combination of vectors, and then what does it mean to say the span of two vectors. So we want to really hone in on these ideas, and let me see if I can jump right in. So notice that in example 2, there's not much work to do here, but notice that they have plotted vector u and they've plotted vector v. Okay? And now what I want you to notice is that there is a way through some linear combination. There is a way of combining u and v given certain scalars such that you can reach this other vector, negative 4, 3. So the idea in a little bit we'll teach you how do you figure out what those scalars would be. But as of right now, the main idea to take away is we would say that the vector negative 4, 3, right? The vector negative 4, 3 is in the span of vector u and vector v. Okay, in other words, it is possible for you to find some c sub 1 and to find some c sub 2 such that if you take your c sub 1 times vector u plus your c sub 2 times your vector v, the resultant, the outcome, will be this vector. Okay? So that vector is within the span. Now, what I want to do to try to hone in on this idea is let's kind of start to look at a different set of grids, right? So we are very used to the xy plane, right? When we're plotting points. Notice now, instead of having these xy planes, notice that we are going to build a coordinate system based on two other vectors. It's important. So I'll write it. So normally the vector, when you talk about vector I or vector j, right? We normally think about vector I, vector j as some unit vector, length 1, and we have that has the following directions, right? So either the I is a length 1 in the horizontal direction, the j is length 1 in the vertical direction, and then that becomes, are you listening? That becomes the xy coordinate system. Now, what I want you to imagine for just a second is forget about the I, forget about the j. What if you were to build a coordinate system based on these new vectors, right? Pretend like this is now your I and your j. Only clearly you're not, if you kind of look at, so just to make sure you understand, so here's v sub 1. Now, if we think about all the multiples of v sub 1, right here would be 2v sub 1, 3v sub 1. We can also go the other way, negative v sub 1, negative 2v sub 1. So you can, for intents and purposes, you can think about this is the x-axis. And now, so since here is v sub 2, And likewise, once you scale v sub 2, you get to 2 v sub 2, 3 v sub 2, etc. All of those combinations would also give you a line. And just like your xy line, these two lines intersect. Only the grid that's created is not that nice, linear, perpendicular grid that we are used to. But nevertheless, I can still plot points, right? I can still plot points on this new grid. For example, I could travel to, I'll just use the language of xy. So normally we would go to the right, a certain distance, and then we would go up a certain distance, and that would be our xy point. But we can travel in the same fashion. We can travel along v sub 1 for a certain distance, and then we can travel along v sub 2 for a certain distance, right? So you can imagine here's v sub 1, here's v sub 2. Now, if you were to plot your point, you can think about reaching this particular point right here, or this point here. Now, to kind of get a feel for what this question's asking, so I'm hoping that this new grid makes sense. Now, notice that there's a vector u and there's a vector w located on this grid. Let me go ahead and point them out. So here is w, and let me find, and here is u. Okay, now the question becomes, is it possible for you to travel along this v sub 1 and this v sub 2 and reach your destination, w? Is it possible to travel along v sub 1, v sub 2 and reach this destination, u? And if that's the case, then how far must you travel in the v sub 1 direction? How far must you travel in the v sub 2 direction in order to reach these points? So let me kind of make sure you understand. So there's some c sub 1, v sub 1, plus c sub 2, v sub 2, right? Notice the scalar c sub 1, the scalar c sub 2. I'm going to begin to give them another name. I'm going to call them weights in a little bit. But for right now, notice the scalar tells you how far you're going to travel in the v sub 1 direction, right? So if you were to choose c sub 1 is equal to 2, then that means you are going to travel in the v sub 1 direction. You're going to travel you're going to travel this way all the way to 2 v sub 1, right? That is exactly what we mean by that. Now, what do we want? Well, we want to be able to reach, let's start with vector u. We want to be able to reach vector u through some combination, linear combination of v sub 1 and v sub 2. All right, well, since we have this nice graph, let's start. Ready? So let's start with the v sub 1 direction to get to u. Ready? So here's my destination. I think you'll grant me that I need to travel all the way to here in order to get to that vector u. So I would need to travel to 3 v sub 1. In other words, my scalar of c sub 1 is 3. Okay, now, again, let's go back to the origin. And now we're talking about the v sub 2 direction. So v sub 2 direction is this way. So clearly we're going to have to think about negative v sub 2 would be this way. And if you want to arrive at this destination u, I'm going to have to travel in the negative v sub 2 direction. I think that makes sense. Now the question is, well, how far do I have to go? Well, you can see that once I get to negative 2 v sub 2, I've arrived at the vector u. So I need 3 v sub 1 minus 2 v sub 2. The result is going to be we have reached this destination u. So I'm going to answer this. We're going to talk about vector w. My suggestion would be to pause the video and just see if you can figure out what linear combination would allow you to reach w, right? What c sub 1 and c sub 2 would be in order to allow you to reach w. And I kind of get it's kind of some guesswork here. But anyway, I'm going to assume that you've either paused the video or you're not playing my game, which is either one is perfectly fine. Okay, let's start with the v sub 1 direction. So clearly I got to go in the positive v sub 1 direction if I want to get to w. And I need to go past 2 v sub 1, but I can't go all the way to 3 v sub 1. So it's got to be somewhere in between 2 and 3. My eyesight's not great. I'm just going to say 2.5, right? So 2.5 v sub 1, or 2.5 is 5 halves v sub 1. Okay, so if I travel to 2.5, that would be the distance I need to go along the v sub 1 line to get to w. All right, now let's, I think you can agree with me that if I want to get to, in terms of the v sub 2 direction, since v sub 2 is moving this direction, I'm going to have to go the opposite way to get to w. Right, so I'm going to have to go in the negative v sub 2 direction. So it's definitely going to be minus, and let's just try to estimate here. So if I had to take a guess, it doesn't quite reach negative 1, so it's somewhere in between negative 1 and 0, and I'll just say a half. So minus 1/2 v sub 2. That will get me to this w. Okay. What are we doing? Why are we doing it? I will come in a little bit. I'll try to sell you on the why part later, okay? I promise you the why is there. But right now, it's just the how. And more importantly, just understand that this is the linear combination part, right? When we chose the 3 and the negative 2, that's the linear combination part. The fact that we can reach u, the fact that we can reach w through a linear combination means that both u and w are in the span of vectors v sub 1 and v sub 2. Okay, I'll give notation for this in just a little bit, but I hope that clicks. I hope that makes sense. Let's let me just pose some questions. So these are not from a textbook per se. These are just some questions that I had to ask myself when I was trying to learn this material. So let's start with some definitions here. So let's say vector u is defined as 0, 1. Let's say vector v is defined as 1, 0. Right? So that's back to your I and your j. And remember that if you're in 2 dimensions, we call that R2. If you're in 3 dimensions, we call that R3, and so forth. Now, so given that information, so given these 2 vectors, I and j, so I can try to draw them, but it's kind of hard with this little tiny graph. But nevertheless, let's start with a basic question. How many vectors are in the span of u and v? Now, do you understand that question? More importantly, when time comes to be tested, will you understand that question? Well, let's find out. So this question is asking, so let me read it. How many vectors are in the span of u and v? Well, the answer to this question is all vectors in R2. In other words, I can reach, see these dots, I can reach any of these points. I just need to travel along the v direction, then travel along the u direction, and I will be able to reach any of those points. So the answer to this question, how many vectors are in the span of u and v? It's all of the vectors in R2. Now, let's think about just, again, using these vectors up here. So thinking about vector u, vector v, is it possible to arrive at some point in space? I'll say that one more time. So I'll list this. So let's just assume that this is the v direction. Let's assume that this is the u direction, and I'll ask my question one more time. Let's pretend for just a second that I want to arrive at the point 1, 1, 1. Right? So you can think of it as length, width, height, over 1, up, however you would like to think about it. But so over 1, so there's some point in space. And this is, again, not very easy to draw, but let's just say that this is that point 1, 1, 1. Now, the question I have is, can you reach this point, 1, 1, 1, through linear combinations of these vectors? Right, linear combination, c sub 1 times u. Actually, I'll stick to c sub 1 times v sub 1. That's the notation I've been using. C sub 1 times v sub 1 plus c sub 2 times v sub 2. Is it possible to reach the point 1, 1, 1? Well, clearly not. Right? I mean, this point here is in space. It has a height. There's no, I mean, these vectors can allow me to travel all along the plane, right? In 2 dimensions, but it's not going to allow me to ever go in the z direction. It's not going to allow me to reach any height. So we would say that this vector is not in the span of v sub 1 and v sub 2. You cannot reach this vector using v sub 1 and v sub 2. Okay, now sticking with this idea, using these 2 vectors, let me pose the question. And at this point, I'm not going to write the questions. So I'll pose them. You may have to pause it and write the questions yourself. But let's assume, so now that you have these 2 vectors, let's assume that I gave you a third vector. Right? Assume that I give you, you're given w, and we'll just say is equal to 4, 5. Wow, so now instead of having 2 vectors, you have 3 vectors. So the question is that I have for you is, does this, giving you this extra vector, does that increase the span? Well, the answer is, does it increase the span? The answer is no. If you already can reach every point in R2, how would giving you a third vector in R2 help you arrive at more, increase the span? Okay, so then next question. So let's forget about the W part now. Let's go back to given U, given V. What if I were to take one of these vectors away? how does that affect your span? So let's say I take away your vector v. What would the new span be? Well, since I no longer have vector v, by the way, I don't, yeah, so since I know, my apologies, in case you haven't already noticed it, I used the language of v sub 1 and v sub 2 instead of using the language of u and v. Not that it changes anything that I've said so far. I'm used to having just vector v with a whole bunch of subscripts. I'm not used to as much to having a whole bunch of different names, u, v, w, all these things. But nevertheless, nothing else has changed from what I've said. So back to what I was talking about. So assume we start off with vector u, vector v. The span is all of R2. I can reach every single point in that plane. But now I take away one of those vectors. I take away v. And now you're stuck with just u. And the question is, what is the new span? What would the new span be? Well, let's think about it. First, we'll draw it. So our new linear combination is just c sub 1 multiplied by u, right? It used to be plus c sub 2 multiplied by v, but I took v away, didn't I? So now you're just stuck with this. Now, this would, since this is u, does it make sense that your new span would be every vector on this line? Stay with me. Let's assume that you chose 1 for c sub 1. Well, you would be able to reach this vector. What if you chose 2 for c sub 1? Well, you would be able to reach this vector. What if you chose -4? Well, you'd be able to reach here. So by having the ability to choose any value of c sub 1, your span, the span is the y-axis in this case. Right? Your span would be every vector along this y-axis. Okay, hopefully it's my hope that this is starting to click. Now let me ask you, so let me pose the question. So if you wanted to be able to reach all the vectors in R3, just like we were able to reach all the vectors in R2, the question is, how many vectors would you need how many vectors are needed to reach all of R3? So if I wanted to be able to reach the point 1, 1, 1, or if I wanted to be able to reach the point, 2, -2, 6, I want to be able to reach any point in space. How many vectors would you need? Well, clearly you need 2 vectors to reach all the points in 2 dimensions. Likewise, you would need 3 vectors to reach all the points in 3 dimensions. Now, can it be any 3 vectors? Absolutely not. Absolutely not. So, imagine for a second that, so here's your u, here's your v. Now, the span, let me give you another vector that's in the span of u and v. Stay with me. So let's assume that I gave you this vector here. Do you notice how all 3 of these are in the plane? They're all in this this plane here. How in the world are we ever going to be able to reach points in space with any height? So yes, you do need 3 vectors. But are you ready? Your vectors cannot be, so there's this other vector w that you need. Let's see if you can follow me this way. So here's 2. You need some other vector because you need 3 vectors to reach all the points in R3 in space. And I'm telling you, it can't be it can't be anything you want it to be. There's some restrictions. So w cannot be in the span of u and v. That's first and foremost. If it was, right, I just got done explaining it to you. If this point here would be in the span of u and v, right? I could be able to go over v and then up u, and I would be able to I'd be able to reach this point. But that's helpful. I mean, that might be helpful in other situations, but not if you want to reach points in space, say along the z-axis. So first things first, w, this other vector w, cannot be in the span of u and v. Another way of saying this is your vectors can't be. Let me see how I want to phrase this. So I'll tell you what. I'll just state it, but then I think I have a better graph to explain what it is that I'm trying to state. So your vectors can't be parallel to each other, right? They can't be scalar multiples of each other. So again, if this is v and this is w, now that would, w and v would be scalar multiples of each other, right? They would be parallel to each other. Well, that's not going to increase your span. 100%. I mean, does that make sense? Like, let's go back to R2 for just a second. If this line here is all of the possible vectors that you can reach with vector u and a scalar, then how does me giving you another vector that's already on that line, how in the world would that help you reach, increase the span? How would that help you increase the amount of vectors you can reach? Well, it doesn't. All right, so I think we'll go ahead and break, and I will see you in the next video.